Hello.
Hello, good evening, sir. Good evening. Hello. Good evening, sir. Vijender, sir.
I'm able to hear your voice. How is my thing? Is it clear? Is it clear now? Hello?
Yes, sir. We can hear your voice, sir.
Okay. Just a minute.
Just 1 minute, sir. Vasanta, madam.
Sir, good evening, sir.
Yeah, good evening.
Ma'am, you can start introduction, ma'am.
Okay, sir. Okay. Good evening, everyone. Welcome to the seventh session of day 4. It is my pleasure to introduce our distinguished speaker for today's session, Dr. Vijender Busireddy Garu, scientist, ISRO, Hyderabad. Sir is working as a in ISRO from 2008 onward. Sir received PhD from University of developing based security models for ad hoc wireless networks and IoT. Previously, sir worked for HP R&D Labs, Bangalore for 1 year. From past several years, sir is working on deep learning and developed real-time object detection methods in remote sensing images. Sir several publications, journals, and conferences included IEEE, InterScience. Sir got Best Paper Award for his paper on applying deep learning methods on remote sensing images. Sir delivered several lectures on security, AI, privacy, IoT to trainers and faculty. His research interests are deep learning, security in wireless networks, trust and Internet of Things. Please join me in welcoming Dr. Vijender sir, his valuable knowledge. Thank you. Welcome, sir. Over to you.
Thank you. Can you give me the permission to share my screen?
You can share, sir.
But
I'm-
option is not showing for me.
Okay, 1 minute, sir.
Yeah, now I just no. Yeah, I got it.
Okay, sir.
Able to see?
Yes, sir. We can see yours.
Okay, thank you. Yes, thank you for the nice introduction. So I hope my audio and video both are clear, right?
Yes, sir.
Yes, sir. So my topic is basically introduction to deep learning. So I will give brief overview of machine learning and why machines need to learn and where deep learning are useful, and some networks. Not in depth of that because my next lecture will go in depth of this network. So I will give you a brief overview of machine learning, deep learning, and what are the different applications in remote sensing and all those things I will show. And apart from that, why deep learning is more like popular, and what means why the performance of the systems or system specifications should be very high when you run the deep learning, and all those things I will cover in my presentation. And the different kind of frameworks also I will cover. So first, I will know why machines need to learn. So why machines need to learn, right? Normally, we have so much youth, young force is there, and human beings are there. But still, why we are teaching something to machines so that some work will be done by the machines. If you say take a program like a set of instructions, and what's like, so for example, if you take searching a number, if you see all this array, right, sequence of numbers, if some number is given to search it, so you have a certain algorithms, right? Standard algorithms are there where directly if you apply like sequential search or binary search, you can directly get the number where it is. Means it's not about the depends on the data. The algorithms are fixed like sequential search and binary search. You give whatever number series and you give a number, it will show detect where that number is. So that is the kind of algorithm, right? But other kind of algorithms, for example, if you take the e-commerce like Amazon or Flipkart, or different kind of like marketing systems, where you need to know like certain information. And like for example, if you see Flipkart, if you open today, for example, some book or something. So tomorrow, if you open again, it will show some recommendations, right? These books or this kind of things. So how this will come, right? This entire data and each and every transactions, it will analyze and it will give some information, right? Some recommendation or everything. So here, if you see, the entire output depends on the data, and algorithm also depends on the data. It's not like if you take the Flipkart, Amazon data, this kind of data, you have to apply a different one kind of algorithm. But once you train the algorithm and everything is fixed, then you cannot apply this algorithm to some other data, right? It completely depends on the data. So in these scenarios, this kind of issues, this kind of problems we need to address. In that places, this machine learning and deep learning is required, where like the entire output depends on the data, and even algorithm also depends on the data, not an exactly sequence of steps. So there, this missions need to learn and do it. Here, if you want to in Flipkart or Amazon, if you want to give any recommendations or anything, if you want to do it in a manual way, a huge task is required, right? But if you automate by using a machine learning or deep learning, the task will be very simple and it will automatically give precisely what the recommendation is. So now you can understand, right, where exactly the machine learning and deep learning should be used. And if you see, right, data doesn't mean a randomness, right? It has some patterns. So what machine learning and deep learning will do, it understands the pattern. For example, if you take the customers in the Flipkart or Amazon, they will not purchase in a random way, right? So in summer, most of the customers will purchase ACs and something like that, right? And in winter, they will purchase tea or coffee, something like that. So the pattern is there, right? If you are purchasing AC, you definitely purchase stabilizer. So such kind of patterns are there. So these patterns are observed from the data, and these patterns are used to make predictions of that in future things. So whatever the data is available, so machines will learn, the model will learn, and it will predict the future. So if you take the classical computer vision pipeline, like you have a algorithm like Swift or Hog or Surf, what it will do, these are in machine learning, right? So what it will do first, you have to extract the features, okay, yourself. That features you need to give it to the algorithm, and algorithm will train. And when you want to give a new data, again you have to extract the same features and give it to the machine. So here you just see only the difference. You only have to extract the features. Here either model or machine will not extract the features from the data. Manually you have to extract the features. That features you need to feed it to the model. Then model will be trained and it will do the things. Okay. But if you do any other thing, like if you take the other thing like deep learning or other thing, where that is not required. So in machine learning, the expertise is required from the human being. Means from the manually, you need to have an expert. If you want to apply a machine learning algorithm in the medical field, then you should have a domain knowledge of medical field. Then only you can apply. So that is the major classical computer. Means up to now, means in the past, before 5 years back or 6 years back, the same thing will be required. So in that case, the features and everything, it's a time consuming. So if you take the computer vision part, you are able to see this cat, right? Okay. So our eyes are seeing like this. But if you see the computer, how it will see the computer? So if you take this part, so it will see the numbers. What each number will show? Each number will show a pixel value that emphasizes what is the what is the pixel value in particular grid. Okay. So what is the problem here? Okay. The problem is like if the camera angle is changing, then automatically it will do. Sorry. So if camera angle is changing, what will happen? The pixel values will change, right? But still we are able to see that this is a cat only. But if you see the like pixel values will change. Similarly, if it is illumination, all cats only, but the system will see in different way. Here also, deformation, right? Normally, how people see cat means it stands on the 4 legs and it will sit like that. But here, it stands on the 2 legs and this slept like this and all these different formations and occlusion. Okay, so background clutter and all those things are there. This background clutter, the color or background and this object both are matching. So all these are problems, right? But from your naked eye, you can easily distinguish like this is a cat. But if the same thing, if you take in a pixel way, like computer, how it sees is a for each and everything, it will take as a different kind of images. But if you see that all these matrices means converting into pixel values, you will also not able to distinguish that which is a cat and which is not a cat. Okay. And another one is the interclass variation, like each will be in different colors. So this is the different data which contains all these different of varieties of data, like 10 classes. So initially, this data is used to train our models so that in universal, we can detect some of the objects. So this is a sample database just to show that some of these kind of data sets are already available. You can see, right, what is this? Kaggle. Kaggle is the one kind of website you have. It has an enormous database of objects. Some are labeled and some are unlabeled. So whoever want to do research in deep learning or machine learning, whatever data is required, you just go into the Kaggle and you can download it. So these are the different data sets. So you just see what are the variations. If you take this one, frog, you have a different kind of frogs here, right? So when you train it, so after that, how you find out is there loss or something like that? If you take a test image and training image, so how it will do? It first do the pixel wise object difference, and then we will add everything, and finally we will get a value. So that we will call it as a distance. So normally loss we will compute like this. So this is the one kind of classifier in machine learning. So which is like a weight. This is the X is the input and plus B is the bias. So how linear classifier will do? It draws a line so that whatever the above the line will be a one class and whatever will be the below line will be a different class. So that is the linear classification. So if you have a multiple classifications, it will be like a multi-dimensional kind of a thing. You can see, right? So I said you, right, how the classical pipeline will be, computer vision pipeline, where we only have to extract the features. But if you take the deep learning based pipeline, so we need not extract the feature. That means you need not have any domain knowledge or domain expertise or anything. You just have to have a data, that's it. So directly data you apply on a model itself extract the features, and then it detects or classifies or anything it can do. So that is the difference between the normal classical computer vision pipeline and deep learning vision pipeline. So you understand, in deep learning you need not have any domain knowledge, but in classical machine learning or anything you need to have an expertise. Okay. So we'll just go through this machine learning. One algorithm I will explain. So this anyway I will do. So with one scenario I will explain. Here, Mr. A is here, and generally he watches the movies mostly, and some movies he likes it, some movies he dislikes it. Okay. Now what we need to do is when a new movie comes, we need to say whether Mr. A likes or dislikes it. Okay. So we have a data, sample data, where which movies he likes it and which movies he dislikes it, that we have a data. And these features we will extract from the data: genre of the movie, hero or director of the movie, length of the movie, time, and language of the movie, Telugu, Hindi, English. So what we will do, we will extract the features from the data, and we will get to know which movies he likes it and which movies he dislikes it. That we will put it here. Like here I have put as the time and action, means genre of the movie. So either action is more and time is more, like that. The both are distinguished. So here red one he dislikes it, blue one is likes it. This is a already known data. Now we need to make a model from this, and when a new movie comes, we need to able to tell that this movie whether Mr. A likes it or dislikes it. So if we take the support vector missions, so this is the one type of machine learning algorithm, which is very famous. So what it will do, it will just draw two linear lines with linear equations, such a way that this margin between the two lines is the maximum. Okay. So in this case, this is the maximum of this thing. So whatever the edge data is there, that will collect as support vectors. Okay. This is a very simple algorithm and very famous and very efficient also. So whatever comes under this side, we will say Mr. A likes it. Whatever comes under this side, we will say like Mr. A dislikes it. Okay. So other than this, we have a nonlinear SVMs also, where this is only single dimension, right? Whatever the left side is dislikes it, whatever the right side is he likes it. Okay. But when you're going in a higher way, like this, like two-dimensional, we cannot two-dimensional. If you take the two like this, right? So other side is also there. So what we will do, we will increase the dimensional. So now in a single dimensional, we will make it to the two-dimensional. And now we draw a line here, right? This is a linear equation. So like that, if it is becoming a complex way, then we can increase the dimension such a way that finally we can able to distinguish the we can able to classify. So there are three types of learning: one is supervised learning, unsupervised learning, and reinforcement learning. So I will just explain about with some example. Here we have a label data. So we have some car images here, and that we say that this is a car, and we have some motorcycle images that we have a motorcycle. So what the features we are taking is number of wheels. Where the car has 4 wheels and the bike has 2 wheels. Okay. So label is this car and motorcycle. So this is a label data. So we can do supervised learning. So we will feed everything label data to the mission, and we are able to classify the bike and car here. Okay. In unsupervised learning, we don't have a label data. We have just a data where we have players and we have their ride points and tackle points here. But we don't know that who is the rider and who is the defender, right? So what do we need to find out here? So if some person came, so we need to find out if the defender or rider. So we need to make a model, but we don't have any label here, rider or defender. So what we need to do, we will use as a unsupervised learning here. So where all data here, whatever we will keep here, right points and tackle points, everything I kept here. So then it becomes like a 2 clusters, right? So now from this, I can say since these tackle points are more, these people are the defenders and these people are the riders. Okay. Now I have 2 clusters here. So that means that my model is ready with unsupervised learning. So whenever new person comes at the red points and tackle points, I will put it here. And I will say if he fall in here, then I will say he is a defender. If he fall in here, he is a rider, like that. So without labeling also, we can make the models here. So another one, the reinforcement learning, which is like a active learning, online learning kind of a thing, where during the operation itself, the model will train. For example, here, if I am giving cat image, dog image, but the mission say cat, then what I say, I will give a feedback to the mission, like this is not a cat. Then accordingly, the model will learn. And next time, if you give a dog, again, it will give a dog output. So what is general machine learning? You say you give the input, then model will give the output. So if any feedback is there, we will give the feedback to the model so that it will retrain it. And again, if you give the input, then again, we will get the output. So there are some machine learning terms are there. One is overfitting and underfitting. Some normally you do have heard. Overfitting means when you train a model, the model works on only the training data. That means instead of generalizing the model instead of learning the model, model is remembering the things. That means it is using the memory. So from the memory only it will give the output whenever you give the new data. So that's called overfitting. That means it works on the training data only well. If you give the new data, it won't be do any good. If you similar way, opposite way, if you come to underfitting, it neither works for the training data nor generalization. That means it's not trained properly. So in the both cases, in the overfitting, what we need to do, we need to put different kind of data for training. So then it model will generalize the thing. In underfitting, you need to have a more data to train. So these are the precision, recall, accuracy. These are the parameters. Some of the parameters like F1 score and all those things. These are the basic parameters to evaluate a model, whether a model is performing good or not. So why machine learning or deep learning is popular in today's era? Even though machine learning and neural networks are established in around 2000, 1990s itself, the main thing is now we have a huge amount of data. So that so much data is there from the IoT or from the internet or anything. So because any machine learning or deep learning is required data, so now data is there. So that's why it's popular. And data handling capabilities are more because we have a large big storages and computing capabilities like GPUs and everything are available. So these are some of the machine learning applications. One is like healthcare for diagnosis from the MRIs and X-rays and everything. So now so many models we have created from the past 7-8 years, brain tumor detection and MRI, some detections. All those things come. Even COVID also we have some people have published some papers on chest X-ray detecting means COVID prone or something like that. So all those models we have prepared. And one thing is sentiment analysis, like from Twitter or anything, we can get the data whether how the sentiment of the area is going and means how people are thinking and like that we can analyze. And another the fraud detection in finance sectors, like any kind of what you say is recently we are seeing so many frauds, right? Like number of transactions. Based on the transactions, we are able to identify whether whatever your incoming call or whatever transaction is coming, that is a fraud transaction or not. So such kind of models. I don't know the e-commerce, as I told in the initial slides, Amazon and Flipkart, it is giving the recommendations on the recommendations on the products. So the recommendation system and everything built on the machine learning and deep learning only. So other than that, you have a Uber, Ola cabs also, right? Where you will get fare dynamically. Even in the aeroplane fare also, you'll get dynamically based on some cabs. You can see, right? Cabs. If it is rainy, all in auspicious day, automatically the price will be very high. Okay, and based on the number of cars available, also the price will be. So all these parameters are used in the machine learning. This is one kind of application. So what is the difference between the AI and deep learning and machine learning? So it's a very small difference. I already told previously. One is like a machine learning, you need to extract the features, whereas in deep learning, you need not have any domain expertise and the model itself extracts the features. Okay. Other than that, this all DL and ML comes under to the AI only. But that means all AI algorithms already machine learning algorithms, deep learning, a subsection of the AI algorithms. Okay. So these are the different applications, AI, and I already told. So one major thing in the training is the backpropagation, right? So when you give some data to the machine learning or deep learning, the model has to learn. Model learning means what? Means what is that learning? Learning means what? Each neuron in the model, the weights in that neurons and the biases on that neurons learning. That parameters are means tuning to the whatever the data we are sending it to the model. Okay, so that how that training is going on, how that parameters will be tuned. That is based on the backpropagation algorithm. Okay, so this is a small neural network where x1, x2 are the inputs, and f1 e to the f6 e all are these neurons, and y is the output. Okay, so it is a two input and single output neural network, right? So when need to start training and initial time of training, the weights will be assigned as random weights. Like by using a uniform distribution, we will assign all the weights to these neurons. Okay. So how the neuron will compute this weights? So if you take these two are the inputs and this is the neuron, so this is the output. So each neuron will be like, it has a one summing filter, like each node this has the weights. So the summing filter E, what will do? It will multiply with the weight, input multiply with the weight, and then it will do the add. So this looks like a linear equation, right? So linear equation, if you put it, so you can easily estimate it instead of writing an algorithm and giving to the neuron. So you can easily expect what exactly the output is. So that's why we have to make that linear into the non-linear element. So that's why we will put as a non-linear element, that is a function, non-linear function, which will apply on this E. So finally, y is equal to this non-linear function of E. So each neuron will compute this one. So it first summing up the weights, and then we apply non-linear element. So other than this, instead of this weights will become zero, although instead of that neurons should not die. So we will add some bias here. Okay. Why bias is required is instead of because these two are the multiplication parameters. So instead of it going to the, we will add a penalty here. Okay. So what parameters will be tuned during the training is here W1 and then W2 and the bias. Okay.
Yes, ma'am.
பிரியாணி போடவா
Please.
வாயில வரல விட்டுட்டு படாத.
Hello.
Sir, I have unmuted, sir. Unmuted, sir. Yeah.
Okay. Okay. So in the back propagation, so I will say just what it will do is, so now we know, right? We have assigned all the random weights. Okay. So here what I will do is in the initial time, this I will just multiply with a sample data. That means I have a training data, right? First I will feed the training data. So then I will compute this F1, Y1. So the Y1 is the output of this neuron. What is the Y1? First I will multiply this weight with the input, right? W1, X1 plus W X21, X2, right? So this again I will apply the nonlinear function. So now I got the Y1, right? Similarly for F2E and F3 also like that we will compute, right? Y2 and then Y3. So now I have Y1, Y2, Y3, right? So now I need to apply these values to this F4 and F5. So when I apply this Y1, Y2, Y3 with this weights and here the nonlinear function of F4. So now I got the Y4 here. Similarly, I got Y5 with the F5 function like this. So now I got this Y4 and Y5. Now I need to get the final output. So I will get the final output F6, nonlinear function of this Y4 and Y5 with this weights multiplied. So now I got the Y, right? So since it's a supervised learning, so this inputs, now I got this output, right? Y. So now what I will do, I will check what is the expected output. This is the actual output, right? So I will check with the expected output. So the expected output is Z, but I got output as Y. So now I will find out how much error I have. This is the error signal. So Z minus Y, this is the error. Okay. Now what it will do in back propagation? So we need to propagate this error back. Okay, that is the back propagation. So I am propagating this back. Similarly, when you're traveling from this to here, I am multiplying this weight with the value, right? Similarly, when I am sending this loss, this error to the back side, so I am just multiplying the same with the weight. So I got delta 4 and delta 5 error here. Similarly, I multiply here, I got delta 1, delta 2, delta 3. Okay. So I got all these three. So now I got loss here, right? So with this, I can adjust this w dash and w dash x to 1, right? This is the new weights. So how I will compute the new weights with this algorithm? So this is not a random algorithm. We have an algorithm here for weight adjustments. So this is the weight adjustment algorithm. So where this is the old weight and the new weight rho into delta 1, which is the loss, and d of f1 a by ap into input. Okay, this is the new weight. So now we got a new weight here. Similarly, same way we'll compute the new weights here, right? Similarly, we'll compute the new weights here. So like that, we'll compute all the new weights forward and forward and forward. Now we got all the new weights here. So once this is done, this one we went back and again we came forward with the weight adjustment. Now again the same training data will apply on this model. So again we will get the new output, right? New actual output. Again we will compare with the expected output. So again we will get some error here. Again that error we will back propagate it, and then we will adjust the weights with the forward propagation, and again we will apply the training data. So like that, the iteration. Now we have, this is a single iteration, right? Whatever we did, like x1, x2 apply, come to actual output, and then again we'll find out the error and go back, and again we will adjust the weights. This is called a single iteration. Like that, we need to do the multiple iterations in such a way that the loss should be minimum. Like whatever we can say, like suppose the loss is equal to 0.01 or 0.001. So if the loss is less than or equal to 0.001 or 0.01, then we will stop that. Okay, this loss, because the loss never becomes 0. Okay, so we need to take some minimum value so that the model has trained properly. So how the training is happening? If you take the gradient descent algorithm, whatever I told, right, weight adjustment algorithm. So that is called the gradient descent algorithm. So it's like a person standing on the top of the hill and he want to come down with a blindfolded. So what he will do? He will put a step forward and he will check whether he is going down or he is going up. If he is going down, he will forward. If he is not going down, then he will put a back foot and again he will try for another step, right? So like that, if he is doing one step, like that he can reach. Means for each and every step, he will check whether he is going down or not. If he is going down continuously, so finally he will reach at the bottom of the hill, right? Like this, right? If he starts here, so finally he will check in stand here. So this is the problem with the gradient descent. What is the problem with the gradient descent? You may not get the optimum minimum value, but you will get the some minimum value. Here, the initial position is very much important. Suppose if you start from here, your algorithm, so you reach this value, right? This is the minimum value. But if you start from here, you reach this value, right? Compared to this value is low value, but over in global way. But in gradient descent, the initial position is very much important. So this position, how you will get it, is a random. Because we are assigning weights are random, right? So this is random. So the random value, what it is fixing, that is very much important. So that's why we'll use a normal distribution in overall way. And on average, you will get a minimum value. So that is the gradient descent algorithm. So in gradient descent, there are different kind of methods. One is the full batch gradient descent algorithm. Full batch gradient descent algorithm means we will apply whole data on the neural network and we will get the output, right? From that, we will compute the error at a time and we will back propagate it. So we will adjust the weights for full batch, means all training data. Whereas if you take the stochastic gradient descent algorithm, for each and every image, each and every data, we will adjust the weights. So that is the difference. And other than that, we have a first order differentiation, second order differentiation also. In the weight adjustment, we have used dy by dx, right? First order differentiation. We can use the second order differentiation also. That is a different kind of technique. So these are the different algorithms. Vanilla gradient descent algorithm is the actual gradient descent algorithm. So instead of putting a one step, in gradient descent with momentum, we will give some momentum. Like at a time, we will jump into the 2-3 steps like that. Okay. So that it is converging fastly. But there are some problems are there, but that is a one kind of mechanism. And similarly, we have an ADAM mechanism, where the slight variation is we will add extra momentum, and as well as we will add some more parameters here. So normally in deep learning, if you train deep learning any in TensorFlow or anything, you can see You heard this name, Adagrad or Adam, something like that. Okay. So next we'll go to the deep neural network. So what is deep neural network? So this I told, right? How neuron will do.
Sorry to interrupt in between, sir.
Yes.
Respected sir, I request to please elaborate about NLP and LLM, sir. Difference between NLP and LLM, sir, and what scenario NLP and LLM are chosen to apply, sir, for application.
Yeah, that I will do. But the topic of this lecture is introduction to deep learning, right?
Okay.
So introduction to deep learning. So I am covering the basics of the deep learning. I will cover. Okay, no problem. I will cover. I will give briefly about 10 minutes. I will do it. No problem. No problem. For NLP and LM, I will answer that question. Okay.
Yes, sir. Thank you, sir.
Okay. So here we can multiply, right? Same way I already told, right? This bias and weights. This is actually a cell body. With this is a nonlinear function, which is the activation function, whether it's a tan H function or anything. So this is the neural network. So if you take the two-layer networks, so how many parameters we need to train during the training? For a simple two-layer network, if you take there are how many layers? 4 plus 2 neurons, right? So each and every neuron here, if you take this neuron, we have 3 weights here. Okay. And here we have how many? 1, 2, 3, 4, 5, 6, 7, 8. 7 weights here. So totally here 8 and here 12 weights. So total 12 plus 8, 20 weights. Okay. And how many biases here? Here 4 biases. Each neuron will have 1 bias, 4 biases. Here 2 biases. So totally 6 biases. So totally 26 parameters we need to train. Whereas in this network, if you increase only 1 layer, so how many it is increasing? 41, almost double, right? So like that, if you take the deep neural network, so many parameters, billions of parameters we need to train during the training season. So that's why you need to have a very complex infrastructure for that. So how we know, what is the, is there any equation or anything for setting a number of layers and their sizes of networks? So there is no such kind of thing, right? So how many layers are there in each and every layer? How many neurons we need to keep? There is no hard and fast rules. It is everything is in trial and error basis only. That's why making a new model is very, very hard and very, very time consuming. Instead of that, if you take any proven model and you can do the customization, so that it will be very easy to go further. So if you take the convolutional neural network, what it will do classify the images, right? Okay. So if you take this kind of image, so how it will classify? So it's eliminate image, right? If you take this, whether it's a boy or is a old woman, okay, and say like duck or rabbit, and this kind of image. So there are some problems with the convolutional networks, okay. So what CNN will do, it will take an image, okay, and it will classify what is the image, and it will give the output as a label. So if you take a cat and dog, something like that, if you give the cat image, it will give the cat. So how it will see an image, we have in pixels, each and pixel value, if it is a black and white. If it is a color, each and every pixel is represented by the 3 values, RGB values. So if you take this image, if you divide in the pixel level, okay, this is the pixel value where the black color will be like 1, like this will be represented. And after that, we will apply filters on this, and finally we will get an output. So this is a simple convolutional neural network. I am just explaining very briefly. So each and every convolutional neural network has 4 steps. The first one is the convolution. Convolution step is like, right, when there is a image is there. So on that image pixel, image data, we will apply some filters to extract the features. Okay, like edge filters or some filters. It's like, for example, if you take this 32 by 32 image, right? This is a 32 pixels by 32 pixels image. Okay. So if you do in a convolution, what we'll do, we will apply a small filter here, either 3 by 3 filter or 4 by 4 filter, 5 by 5 filter. So what we'll do, in each and every pixel, multiply, and then we will add it, we will get a single value. So the single value will again make as a 2-dimensional matrix. Okay. So that we call it as a feature map. Okay. Here I have applied six filters here. So that's why I got 6 feature maps. Okay. Again, if I apply a convolution, again we will get some more features. The number of features we are getting, feature maps will get, depends on the number of filters what we are applying on the image. Okay. And next step is the max pooling. So why max pooling is required is when you apply a convolution, it reduces some further. Suppose if you add some some extra values at the end, like we add it at the edges something 0, 0, 0s. I mean, append something, that there it won't reduce any image size. Okay. But if we want to reduce the image size, then we apply max pooling. What max pooling will do? It is also a filter like 2 by 2 or for something 3 by 3 or something like that. What max pooling will do is in the 3 by 3 area of the image, what is the maximum value of the pixel value that it will take. So what will happen? It reduces the image size. So why we are reducing the image size is, I already told, right? CNNs, it has some billions of parameters need to train. That means you need to have a lot of complexity. Computation power is required. So if you are giving it big images and more number of pixels for training, so what will it take? More time, right? More time, and it consumes more power. So max pooling, what it will do? It reduces size. So even though if you reduce the size also, the features won't. The features will not be like much affected, but still we are able to get the much accuracy. So that's why the max pooling is there. And next is the flattening is generally will it is at the end. So what flattening will do is whatever the feature maps are there, that multidimensional, right? This is a multidimensional matrix that we will convert into the single dimensional matrix. So that is the flattening. So that means it will become like a single dimension. From there, it is a fully connected neural network. So whatever I showed previously, it is a fully connected neural network. So finally, how many outputs are there? That many neurons only will be there in the output layer. So this is the general overview of CNN. So anyway, in the next lecture, we have a CNN separate topic. So that's why I'm not going into it. So these are the basic deep level. One is the LeNet. LeNet is basically for the classifying the digits. Okay. And next is the AlexNet is very popular with the 8 layer. It has 60 million parameters, right? So it will do millions of parameters we need to train. So 60 million parameters.
Sir, I have one question.
Yes. Yes, please.
Sir, you told that it converts the image into symbol dimension. I'm not getting, because image is generally multidimensional. It is in the form of matrix.
Yes. Here in the flattening, I am telling. So here you can see right in the image, this is the multidimensional, right? Here. My cursor you are able to see, right? This is the multidimensional. So from that, this entire multidimensional I am converting into single dimensional. Okay, this is a fully flattening. So from this onwards, it will become like a neural network. You can see, right?
Okay.
From this flattening will be like this. From this onwards is a fully connected network. So the output layer is number of outputs. Okay. So this is the flattening. So this entire thing multidimensional into the single dimension. Here it is not an image. It may be image only, but we will not call it as images. It will call it as feature maps. So each and every pixels, each and every this map contains one features, right? So this entire features I am making in a single dimension. Okay. And this is AlexNet, and next is the GoogleNet, which is a very popular one. Other than GoogleNet, we have a ResNet also. The ResNet uses the residual thing where I told you, right, when you apply convolutional algorithm, the image size reduces, and further if you apply max pooling, the image size reduces, right? So if for small objects, there may be chance of that evaporate during the course of training by the, so when it's moving from the starting to the end of the network. So what ResNet will do is, whatever the previous network, some important features, it will forward into the next layers, so that the small objects or any unknown objects, it won't means the features won't be erased completely or evaporated completely. So that is the advantage with the ResNet. So in the ResNet also there are different layers are there. So but presently GoogleNet and ResNet are more popular. Okay. So even if you see here, AlexNet uses 8 layers, but it is 60 million parameters. But GoogleNet has only 22 layers. It has 4 million parameters because of inception layer. Inception layer is like a one-dimensional layer. So what it will do is it has a only one-dimensional means only single filter value, but it has a very depth. Depth is equivalent to the feature maps dimension of the image. So we will get only one output. That means multi-dimensional feature map into it converted into a single dimensional feature map. So that's why the number of parameters got reduced here. So you can block the CNN images also, CNN networks also, right? For example, if you train the model with Trump image, so you cannot distinguish it, but as a human being, we can distinguish this is a chicken and this is Trump like that. But if you give same images to the CNN, it may not give accurate images, accurate output. Similarly, if you take this dog and cookies also, like this, right? Here and this one and this one and this and this. So it looks similar only. So where you can block the CNNs here. And other than this dog and what to say, Wapa, something you talk about. This one.
Hello, sir.
Yeah.
Hello.
Tell me, ma'am. Yeah.
Good evening, sir. So, how to calculate
Yes.
the future map? Can you tell me the calculation, sir?
How to compute the feature map?
Yeah. You have to mention some values for each and every pixel map in top of the layer, sir. How to calculate? How to get the value from previous layer, sir?
How to actually, so I will repeat the question. So you just let me know whether the question I understood properly or not. So what you want to know is how the convolution layer computes the feature maps from the image.
Yes, sir.
Yes, right? Okay. So
Yeah.
that only, right?
Yes, sir. The first feature
Okay.
map size 6 into 28 into 28. So second feature map size is 6 into 14 into 14. How to get the value from the previous mapper?
Okay. I will tell.
Yeah.
Okay, I will explain.
Yes.
No problem. So
Okay, thank
here
you, sir.
the initial size of the image is 32 by 32. That means 32 pixels in the column and 32 pixels in the row. Okay. This is the pixels, 32 pixels by 32 pixels. This is the input image. And this small box you are able to see, right? This I am calling it as a filter. Okay. Which is a convolution filter here. So what it will do is it will start from here actually. Okay. If suppose this is a 5 cross 5 matrix. Okay. 5 cross 5 value. So initially what will happen, all this will be in the random only. Okay. The 5 cross 5 matrix will be assigned as a uniform distribution random values. So once I keep it here, this 5 cross 5, so what it will do is the corresponding pixels, the dot matrix between these two data. So that means the pixels and the values in the this filter will be multiplied first, and now we will get like almost like 3 cross 3 filter. We will get the 9 values, right? And that 9 values we will add it. So we will get a single value, right? That single value will be placed here. And then again we will shift by 1, and again we will compute the convolution here, like multiply this filter with the whatever the data in the image, and we will get a single value that we will keep it here. Like that again we will shift one more, and again we will keep it here. So like that we will go. Okay. Understood? Not understood?
Yeah, okay, sir. Thank you, sir.
Okay. 1 minute. I will tell.
Yeah.
I will see whether this has data or not. Okay. So this is the input image, and this is the filter, right? Okay. This one. Wait. Okay. So if I kept here, this 3 by 3 matrix will come here, right? So what will happen? This 0 into 0, 0. This 0 into 0, 0. 0 into 1, 0. 0 into 1, 0. 1 into 0, 0. 0 into 0, 0. 0 into 0 and 0, all are zeros only. So all I will multiply and then I will add it, and finally it will come into here, 0. Okay. Then I will shift by 1. Now the filter will be like here, okay, in this box. So now again I will multiply dot matrix, this 1 into 1 will get 1, right? So when I multiply each individual pixels and then I will add it, I will get 1. So that 1 comes here. So like that, I will shift here, and I will, after this coming here, I will shift down. Finally, sorry, I will reach here, right? This is the last one. So this value come here. So this is the feature map for this filter. So like that, if I apply 6 filters here, I will get 6 feature maps for this image. So this is actually happening. Okay. So here I am applying 6 filters. So since once I apply filter, the image size will reduce. There is a formula is here. So it will become like a 28 by 28. This 2-dimensional size is 28 cross 28. And we have a 6 feature maps here. So again, I apply a convolution filter here. And again, it reduces to 14 cross 14, each feature map. Because each here, suppose 3 by 3 is applied, we will get a single value, right, from the 3 by 3. So that's why the image, the feature map size reduces. So here also I applied 6 filters here, so I got 6. So here I applied 16 filters here, so I got 16 feature maps. Here also 16 feature maps because 16 filters I applied, like that. Maybe next lecture it may be covers deeply, I think. So this is one. And this is the comparison of the different networks. If you see the round bigger means it's a very heavy models. And you can see ResNet 152, and this is the top one accuracy. If you see Inception V4, it's the Google Net, and then ResNet 152 and 101, which are in the top positions.
Sir, one question.
Yes.
At each layer, which filter to apply, how it is decided? Because ultimately we are saying
It is
that
not
we
decided. No. Yeah, that's what. So initially, all values in the filter is randomly assigned by using uniform distribution. During the training, the values will be set.
Okay.
So next one is the detection. Yes. Detection and segmentation. So what is detection? So if you take this input image, what is the classification? The entire image, it will say what this image contains, like a rider or person or something like that. If you want to do object detection, it's further localized like this. Where is the motorbike exactly and where is the person exactly? Okay. This is somewhat localization. If you come to the segmentation, it is further localization, like pixel level localization. So it exactly tells which pixel contains what. Like this is the person and this is the motorbike. So as we were going from the classification to detection and segmentation, you will get a precisely, means you will get localize the targets, objects. Similarly, the complexity increases from the classification to detection to segmentation. Okay, either computational complexity and model complexity, all those things will increase. So if you see the detection is also like a 50% of classification only. So if you take the RCNN, this is called a region-based convolutional neural networks. So what it will do is it will first get the regions from the image, means which regions are the probable regions for the objects. And for each and every region, we will apply a convolutional neural network. Each and every region, we will apply a CNN. We will classify it what it contains. So this contains person. So this contains a person here. Like that, this is the horse. Like that, it will identify. Once it comes at the end, whatever the wrapped region is there, right? So that comes as a bounding box, and it will say this is a person. So ultimately, how it looks like? It looks like this is a person and this is a motorbike. But what is happening? Initially, we are cutting the images. It is wrapping the images. Some like 2000 regions or 200 regions, 2000 images will make for a single image. Each and every image is subjecting to the classification, and finally we're getting the output. So that is the object detection in the RCNN model. If you take the you only look once, YOLO, there are different versions are there, but what the basic YOLO will do is, instead of doing the number of images, it will make a grid. S by S cross S grid it will make, and each and every grid it will check what it contains. So dog or cat or anything. Suppose this contains dog and this contains dog. So then what it will do, it combines the neighbor grids, so that finally it makes a single object. So this is how the output is. So that is the difference between the RCNN, region-based convolutional networks object detection, and you only look once object detection. Like this, we have a SSD and all those things. Even YOLO also, you only look twice is also there, and YOLO also there up to V5 also there, version 5 also. So each one has a number of layers are different, and all those things are different. So this is how like old crow and modern crow. So how it drinks the water, just to show like how the technology is growing nowadays. So what are the different deep learning softwares we have? Before that, if you see the computer here, so why the deep learning is, very popular now, we have a computational way also, we are much more technology, much more increased. Like we have a GPUs here. So each and every computer, you can see here, the GE4, GTX, these are the GPUs here, okay? If you see, this is the CPU. Okay, previously means normal systems will have a CPUs, and now present if you want a graphics card kind of a thing, which is called a GPU. Other GPUs also there, general purpose graphical processing units. So that is also there. That is called the GPU also. These are the GPUs. Okay, if you see here GPUs. So what will contain GPUs contain? GPUs also contains like a some cores, similar like CPUs, but the system is different. GPUs are like a SIMDs, like single instruction and multiple data. Like only all cores will execute only one instruction on different kinds of data. Okay. So basically, NVIDIA is very popular for GPU manufacturing, for graphics or anything. NVIDIA is only the now making all these things. So if you take the number of cores, so CPU to GPU difference, this 4, 10, like that, it will be there for the CPU, whereas GPU you can see like multiples of 1,000. Presently, we have H100 GPU card. H100 GPU card has 12,000 around cores. But whereas now highest CPU, Intel CPU has 40 cores. So what is the difference between the CPU and GPU? CPU, each core independently works. Like each core works on different multiple instructions and multiple data. Each core works on its own instruction and its own data. But whereas if you take the GPU, each core runs only single instruction. If you run a single instruction, each core works on that single instruction only, but the data may be different. That is called a single instruction multiple data in computer architecture. For example, if you take the matrix multiplication, if you apply this in a CPU, so what will do, you will put an iteration, right? If for loop, through 2 for loops or 3 for loops, we will put and we will run each and every element. So what is the complexity of this one? Order of m into n, like order of, if all are n cross n matrix, you can order of n cube, something like that. Okay, that is the matrix multiplication in CPU. But if you take the GPU, I will write a like only a cross like matrix multiplication of these two. Only one equation I will write, one instruction only, and I will just give each core assign say this data, like first core take this data, second core take this data, third core take this data, like that. Okay, similarly like here. So when I run an instruction, so all cores execute that instruction, but different data. Means first core executes on this data and second core executes on this data. So in a single cycle, I will get the output. In a single cycle, I will get that. That is the difference between the CPU and GPU. Okay. So GPU will write in a CUDA language or OpenCL language. This is a different language. So only the problem is all model will be trained in here, but the data, everything will be in the hard disk or in the main memory. So this is the main bottleneck here. How to, because GPUs are very fast, but the bus between the this hard disk and the GPU is very slow. So the transfer of between data is very, very slow, right? So that is the bottleneck here. So these are the different frameworks, PyTorch and TensorFlow, Keras and CNTK, and different products are there. But what is the presenting? Presenting a PyTorch or either Keras or TensorFlow are using it mostly. These are the deep learning framework. So what framework will do? Framework provides you APIs or like APIs and software to train your models or to train or infer your models. So, and one more thing is you might have not known like how to programming a GPU or not GPU by using for deep learning framework, because deep learning frameworks are developed such a way that it uses the GPU. That means some of the part of the code has developed in CUDA language or something like that. So if you take the TensorFlow, so the TensorFlow code looks like this. So this placeholder is like a variable kind of a thing. So it is like a variable to store the data. The data is in the shape n cross d, and each value is a floating value. So like that, this xy is the input and w1, w2 is the weight. So we'll create like this. And then we do matrix multiplication of x comma w1. So even the two matrix in a single iteration, the multiplication will happen because it's a GPU code. So all those things will be run here. So the initial thing is this code. Anyway, most of you know Python. So this we need to import TensorFlow as TF. This is the module. And this is the computational graph we are defining here. And this is the gradients we are computing. This gradient is by gradient descent algorithms I told you, right? So from that, we need to get the loss here. And this is the training. So this just.run, if I run it, this will give the train, and loss automatically computed up to, once loss is minimum, automatically it comes out of this training. So this already I told you, right? So in the TensorFlow, how we'll see that how the model is training. So it provides a tensor board here. So the tensor board will show the graphs here, what is the loss, present situation, and everything, each and every iteration and all those things. From this, we can see, like, because when you put a training, so it will take almost like 1 or 2 days, right? So for that time in between, whether it is going properly or not, by using these graphs, we can easily see whether training is going properly or not. So I will provide you some of the applications here. So if you take the remote sensing images, it depends on the image, right? The spatial resolution to spectral resolution. This is a spatial resolution, so which contains 0.5, 50 centimeter, 50 centimeter. And if you take the meters, you cannot able to see what the image contains. So this is the difference between spatial resolution. And if you take the spectral resolution, it's a black and white color images. So this is a 60 centimeter image with a color, right? So all able to, you can see green, grass, and everything you can able to see, right? So how the experiments will be done here? So this is a label image tool, right? Where you can prepare your data sets. Like if you want to train a model, you need to have a training data, right? So how you will training data for supervised learning, you need to label it. So how we will label it? So this is the image. We have to load it to the label image tool. And you have to use the cursor, and just to drag and drop, it will create a square box here. And after that, we can apply what this contains. So finally, it will create a text file for this image with the same name. So that labels, once the dataset preparation, everything completed, then we will further training. So we have trained with the 2 lakh steps by using K40 GPU, which has a 2,800 cores here. So these are the initial results. So if I see this, the Bombay airport, so I can able to detect the airplanes here properly. This is a small image, right? If I give a big image, so then the problem comes actually. So it is not able to identify the objects properly. So why it's not able to identify the objects is each convolutional neural network has a fixed kind of input. For example, if you take the Google, it will take a 224 cross 224 image only. If you give the more image, more pixel size, bigger size image, so what it will do is it will sketch the image or it will crop the image and it will feed it to the CNN. So similar way it is happening if you squash or if you crop it. So some objects may miss, right? So because of that, it's not able to identify properly. So what we did was, instead of applying a big image, so one more thing is looking like objects, like if this is a flying aeroplane, And this is also aeroplane, but it's like a looking like object, right? So it's not able to identify what this object is. So, but it's looking like a aeroplane object, so it's detected as aeroplane only. So we have proposed a method. What we will do is during the training data preparation itself, we'll tile all the images at fixed size like 1024 cross 1024, something like that, and we will labeling the aeroplane images, and then we will do the training. And even during the inference also, we will tile the images, and each and every tile we will infer it, and finally we will combine all the images. So we will get an output, single output. So same way we did the experiment with 1024, 1024 image, and with the two classes, one is aeroplane and another one the miscellaneous class. So that whatever are not aeroplanes, false alarms kind of a thing, we will put it in miscellaneous, so that lookalike objects will not come as an object, come into the aeroplane objects. So we did the same 2 lakh steps only, which took almost like 1.5 days, something like that, for training. So now if you see apply a bigger image, so still we are able to identify the image objects here, right? So when I zoom it, you can see, right, it is all green boxes you can see. So like that, we have given different test images to check our model performance. These all are contains different airports. So it's a bigger airport also we can given. So we are getting, but the only this one is like this hangar also looks like an aeroplane, so it still has some false alarms here. Okay. And this is another image. So you can see, right, from this image to this image, the brightness also changed, but still we are able to identify the objects. This is a Kuwait airport. And this is also the brightness is different, but still we are able to identify the object. And this is another image. You can see the sizes of the images also, right? The size of the 6397 by 9245, and this 22398481, and this is the bigger size image, and this is still bigger image, 7140 and 5123 image, this one. And this is one more image where we can identify the aeroplanes here. And this is the results here. We have computed precision, recall, and accuracy, overall average, and for each and every image also we have computed. So this is the image, this is the yellow is the actual proposed model with 2 classes. We're able to get a good precision and accuracy values for that. So this is with color images, multi-class object detection on Google Images we did it. So here we are able to identify the ships and everything. This is like we have created some more models. So this is a kind of deep learning applications in the remote sensing. So this is the segmentation. So where we made the building segmentation. So whatever the buildings are, that is segmented with a color, right? This is the foreign data, so we are able to easily segment it. But Indian data, it's very difficult to segment the buildings. Okay, because the distance between building to building is very low, very less, right? So, and here one more thing is in the object detection, it is a ship, but the detection box is very high, right? If you compare computer view, intersection over union, so you will not get a good this thing. So that's why what we do, we further localize it. So when within the object only, we'll get the bounding box here by using some attention model. So this is the problem, right? Here it is detected two separately, or detected as a single ship, something like that, we don't know. So by using this attention mechanism, we are able to detect individually. So we get the accuracy also, good accuracy. And other than this, this is a like 65 centimeter data. But if this is a 56 meters data, this is also still ship data only. You can see all these 2 pixels are there, right? This is also ship data only. So still we are able to identify because the wakes are there, right? See, when ship is moving, the water will make some wake, right? So that waves also train. So because of that, we are able to identify the ships here. So other than that, I can say that even though big systems are required for inference, means only for detection or inference part of a thing, we can put in a small boards also, embedded kind of boards also, where we have a Xavier boards, like NVIDIA Nano boards, Xavier boards, TX1, TX2 boards, all those things are very small boards, like it's like a 3-inch by 3-inch kind of a small boards. So it has a small GPU also. So all our models, we can keep it in these, and we can we can do inferring. Means we can put the images into it, and we can do the inferencing, and finally we can store in the database also. So that is the embedded way also we can do it, other than that applications like edge computing. How is now it's popular, very popular in it now. Like all PhDs and everything is coming in edge computing way. So these are edge computing devices where at the end of the sensor itself, we can able to predict, and we can send inference to the only the base station. So such kind of things we can use like in this inference also. So other than this, we have applied a speech to text also. This VOSK, Novels boards are there where it is only for the speech boards. So that contains VOSK tools where if you give a speech, so it will convert to the text. So the text will connect to the query and to query the database to get such kind of analytics on the data. So after the inference and everything. So such kind of things also possible with the deep learning. This is the one kind of application using the deep learning algorithm. So these are the hardware we can use. This is the AJ Xavier boards, NVIDIA Xavier board, which contains both CPU and GPU. And this is the Novels board for the speech processing. This is the Novel boards which contains the speech APIs inside built it. So it is actually optimized for the speech processing. So there we can use it. So these are the one of the application where if you apply some query here, so we'll get an output here. Okay. This is what this thing. This I will come once again because one more question I had there. LLM, difference between LLM and NLP. At the time I will come here. So another one is the face recognition. So in the face recognition, what we'll do? First we'll crop the face. Okay, we'll detect the face. Once we'll detect the face, then after that we will recognize the face. So how we will recognize the face? We will extract the features from the face, and the features we will classify with the existing data by using the STM classifier. So from that we will get the best match, and that we will display as a face recognition. So here I am able to identify this small thing. So we made a small face recognition application where, like for attendance center, where it takes the data and it displays information from the database. Okay. So other than that, in the Chandrayaan 3 also, we have used some machine learning models where we can see that these are the parameters. This in machine learning, what we need to do, we need to put before itself, right? So these are the parameters we need to give to the machine learning model. So with these parameters, model is created. So from that, it identifies these sites for landing sites for safe landing. So in that, one of the site is selected as S3. At that site, the Chandrayaan was landed. So this is some of the images of the Chandrayaan. So the Pragyan rover has moved entirely in autonomous way. So the front camera also has a model where it detects the boulders or craters or anything. So first it went here, it found a crater here. So it came back and moved this side, and it found a crater here, and again it came like this, and one more crater is there, again came back and went like this, right? So this entire thing is not operated from the Earth, from the mission control center. It is automatically done it. Okay, that's what I want to say. And one thing, so there is a question, right? NLP, difference between NLP and LLM. So if you take the NLP, so I will say, just give me 1 minute. I should have something to show. I don't know I have whether thing or not. So if I have, I can better explain what is exactly. Just a minute. I think I don't have. Okay. So I will explain just like that. Anyway. Just give me 1 minute. Let's see. Okay, so what is the difference between NLP and LLM, right? NLP and how it differs, right? So in the natural language processing, so what we are doing is, so in this scenario, and I will explain. So whatever the data, whatever input data, whatever results is coming, we are putting in a database here. Okay. So now we need to apply a certain thing like a query or something like that, where we will get an output, get an answer from this database, right? So in the NLP, if you use it like specific to this one, right? So what I will do, I will just convert the text and text to query. So I will get an precise output. For example, like this: how many airplanes are present in the New Delhi? It will just like that. It will give this output. Okay, this is this many are there at this date and everything. But if you use the LLM, what large language models will use, it extracts the large language model. How it is probabilistically it will do, right? So it learns the data and each and every vocabulary words it puts in a dictionary. So it will take a one by one word and compute a probability, compute a conditional probability of what is the next word conditional probability, and based on that it will put it. Okay. Here I get the information very accurately from the database as it is. But if you use the LLM, you will get an approximate data, like blah 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 data will get it. Okay. Instead of a single data. Just 1 minute. So 1 minute. Okay, I will just check whether it is there in this. If it is there, then so we made both LLMs and this thing NLP. I will just show the difference between the what is the output we are getting it. So this is one more SAR data we have taken. So SAR data you might have known. This is radar data. So this also ship detection we have used it. So we made a small thing, image summary, which uses both NLP and as well as a LLM. So what we'll do is, I told you, right, each and every input, output, we store in the database. Okay. So finally we'll give a query, right? So if I give this data, so what we'll do, we'll get an output like the 2 engine reference and all those things we'll get it. So once we get all those data, so that I'm combining and make a summary here. Okay. This is like an image summary, not like an image caption. So for this image, I will get almost like 1.5 page caption. So from that, I need to make a meaningful of it, right? So above is the NLP model, natural language processing model. So what we did is we have applied some algorithms here. From that, we have extracted, this is the information is available from this image, very crisp one. Airplanes are parked without hangar, single engine airplanes are parked in the airport, 2 engine airplanes are parked, commercial airplanes are there. So only these are there, this is only there. If you take the below one is the LLM Llama model. So when we given this entire captions to this Llama model, so we get this kind of thing. It's like still information is there, but it's like a vague information. Like all the one repeatedly states airplanes are parked in various configurations at the airport and all those things, like blah blah information. So even one more thing I can say, if you take LLM model, it won't give this kind of thing. Like on this date, this many numbers are there. LLM will not give. Whereas if you take the NLP model, there we will get exactly the output here. Okay. That is the difference between the LLM and NLP. This is how we made a recent cluster computing for all the things. So this is one more kind of board here. Okay. So I told you, right, this is a simple Xavier board, right? Only one board. Like this is a cluster. This is also small board only. This is a 4-inch by 4-inch board only. It contains 4 Xavier modules. Whatever the Xavier board on board I have shown, right? Here it has a 4 thing. Okay. One is the master here and other 3 are the workers here. So once you give the inference to this master, it will assign to a particular worker and it will make done. Okay. So we have used the Kubernetes here for this. So this is also called the edge cluster board. So with the Kubernetes, 1 master node, 3 worker nodes. So we are able to do this kind of things. Okay. So I think with this, I am concluding this presentation. So if you have any questions.
Thank you so much, sir, for the elaboration. Thank you so much.
Any queries?
Good evening, participant. Do you have any queries?
No, sir. Thank you. Very informative session, sir.
Thank you. Thank you.
Sir, I have one query.
Yeah.
Sir, like we read some research papers in which they have mentioned the accuracy achieved is 99%, 99.5% by applying convolution neural network. Sir, is it possible to achieve such type of accuracy in real world?
No. See,
Sir,
I told you, right, that face recognition kind of application you will not get at all 90% also. So, and another thing, any application if you say, because so how the papers writing is, they will have a training data. So the training data, they will feed it to the model. Okay. And they have a testing data, also similar kind of training data. It's not like a real-time data, right? So when you say the testing kind of a data, so obviously you will get a better performance. Okay, even though it's not included in the training, but similar kind of data, right? So you will get a better performance. But when you will see actual performance, then it is operationalized. For example, if whatever the remote sensing I told, right? So here we got a very good accuracy and everything. But when we deploy at the user sides, okay, the client side, We got almost like here we got 80%, 85%. We thought okay, claps and everything, but there if we put it, then again it went to 55% only accuracy. Okay, so what we did again, we trained with their data and real time. So it is a continuous process, but you will never get a 99% or 99% anything. It's like in between 85%, 80 to 85% is very good enough in the deep learning. Okay, in the operational mode. So, but
Sir.
to achieve that also, you need to give regular training.
Yeah, sir. Yes, sir. Sir, that means I should not believe on those readings mentioned
That
in the
maybe
paper.
like there will maybe some assumptions will be there, right? Maybe you can read paper properly. So I am not saying like all papers. If you take any transaction papers, good transaction papers or general papers, you may get very good, accurate or reliable kind of outputs or anything. If you take any conference papers and read conference papers, that I don't believe all those things. So if you read transaction papers and some journal papers, very good peer-reviewed journal papers, there you will get correct information and reliable information because there a lot of scrutiny will be there and reviews will be there and all those things. So it will be better if you read that kind of papers.
Okay. Sir, one last question. Sir,
Yes.
I recently started working in deep learning and I am looking for some like research problems. So I read a lot of things like we can apply deep learning models on different types of image data sets like brain tumor data set or you can say retinopathy data set.
Okay.
So,
Okay.
sir, what are the things like what type of research we can do in this thing like
No,
in
actually,
image analysis?
yes. Now the deep learning on the image kind of a thing, it's become like a world. Means already went to the saturation model. So there is nothing like only like just applying the model. So now we can have attention models and all those things in the convolutional network also in object detection also. That new models have come, attention layers, where we can include some more parameters so that we will get a more accuracy kind of a thing. So ultimately, our goal is like get good accuracy, right? You have to take the data and apply a model on it and customize the model, so that you will get a good means good accuracy. So that is the one thing. Means like at new layers we need to add such kind of a thing is the research thing. Where in the image side, if you come to the data side, you can work on this vision based language model like large language models. It's like if you give an image, it will automatically convert to text and will give an output. Okay, so such kind of new models are coming. So instead of going into this brain tumor and all those things, if you concentrate on that thing, that will be better. And other one is security, where intrusion detection systems and all those things, where you have a data, you can use a deep learning model to get like for new data, whether it's any intrusion is happening or not. Such kind of models also you can develop it. That is a security. It's a new coming thing. So that is a new research area, I can say.
Yeah. Thank you, sir. Thank you so much, sir.
Thank you. Okay, thank you, and thank you for the organizer for the giving opportunity.
Thank you, sir.
Thank you very much.
Sir, wait for 1 minute.
Okay.
Ma'am, Vasantam, madam.
Sir, I'm here, sir. Thank you, sir. Thank you, Vijender, sir. It is an absolute pleasure to extend our heartful gratitude to Dr. Vijender, sir, for his enlightening talk on deep learning concepts. Your in-depth explanation of machine learning applications and what will have, why we need to go for back propagation and what are the benefits we are getting means how to calculate the error rate and all these things you have explained in very clearly, sir. And also the softwares of deep learning and the framework of deep learning, TensorFlow, and differences between the LLM and NLP. Your insights and knowledge have truly inspired and enlightened us. Thank you so much, sir, for spending your valuable time with us. Thank you once again.
Thank you, ma'am. Thank you.
Yes. Dear participant, next session will start within 2 minutes. Good evening, Dheeraj sir.
Yeah, good evening.
Asanta madam. Sir is ready to deliver his lecture. Please could you
Okay.
introduce him?
Okay, sir. Okay. Thank you, sir. It is my privilege to introduce our esteemed speaker for this session, Dr. Dheeraj Garu. Sir is currently serving as an assistant professor in the Department of Computer Science and Engineering at Mahindra University, Hyderabad. Sir worked as a software developer in various organizations across the USA and India, gaining over 12 years of experience in IT industry, R&D labs, and government organizations. Sir is a recipient of Germany's prestigious DAD postdoctoral fellowship. Sir earned his PhD from NIT Warangal and completed his master's degree at University of Central Missouri, USA. With several impactful national and international publications, he is active contributor to academia. Sir is also serves as a reviewer for reputed journals and conferences, including Computers in Biology and Medicine, Engineering Applications of AI, the Journal of Supercomputing, Packard, and DASFA. Additionally, he is a program committee member for Packard 2025. Sir's research interests are natural language processing, healthcare, deep learning, large language models, explainable artificial intelligence, and bioinformatics. I extend a heartfelt invitation to Dr. Dheeraj sir to kindly share his invaluable knowledge. Thank you, sir.
Yeah, thank you very much, Professor. For inviting me to the talk. So, yeah, I'm going to share my screen, entire screen. So, I think, is it visible, my screen?
Yes, sir.
Okay, perfect. So, yeah, so today's talk, okay, all right. Today's talk, we are going to discuss about the foundations of NLP. So that, we have the various concepts while dealing with the foundation, but this will be the advanced level. However, this is something kind of the foundation, but we are going to be understand about the intuition behind multi-head attention in the transformers in the while applying an AI. So recap, before entering into the these type of the attention mechanisms, so these are the background of the attention mechanisms such as language modeling, recurrent neural network implementation, and applications of RNN language modeling using LSTM, sequence to sequence learning attention. See, these are the some kind of the models which are going to capture the sequential dependencies. These words which are depending upon the in a sequence. So you take one example while representing the RNN. So we have the n number of RNNs depending upon depending upon the length of the text. For each RNN, we are giving some input. You can say some word, and we will get some outcome. And we are capturing those outcome, and we are inputting to the next timestamp. Next RNN, and so on and so forth. This is one kind of the sequential structure. Where major idea behind application of these RNN based networks such as LSTMs, BiLSTMs, GRU. So this is one kind of the pre-rig sequential structures, and then preceding to that, I mean, this is kind of the successor transformer based, attention based modeling, where we are going to be captured these parallel dependencies, not only the sequential one, but if we run these takes in a parallel, in which we are storing these patterns in each head representation. So that's how we cover the concept here. And so the intuition behind the attention, so the weighted sum is a selective summary of the information contained in the values. So the idea of the attention is to obtain the fixed size representation of an arbitrary set of representations such as a value and depending upon the query. So the major idea is to capture the feature matrix over there. So during the, after completion of the encoder architecture, we are going to capture, during the encoder channel also, we are capturing such feature matrix. So these could be like the fixed size representation, which we call. So in that, we are providing some weightage over there in order to understand which kind of the elements. See, if we pass the words, it's going to be converted into numerical vector format. We term those as the elements. So we are going to compute using the various type of the vectors over here. Such as the query, key, and value. So these are something kind of the weightage given to the each tokens. In a higher level, I'm explaining you. These are one kind of the black box in nature. So hidden patterns over there. So actually, the query represents the token which we are looking for, and the key means the corresponding words which plays a crucial role in order to identify my current query, and the value means the dot product of these query and key related things. So ultimately we will get the product value, dot product value, which refer as the value vector. So which is used for scaled out computations. So do we have enough attention? This is the main ideology. You can see I gave my dog Charlie some food. So what attention mechanism going to do is, so we have focus on these token such as give. So this will be the query, and the near related one means the keys. So how this shows the impact on near related one, and these features going to be create a major impact on predicting this word. So such as we represent relevant to, we pick this one, and we correlated with we move forward such as 1 attention and the 2 attention and the 3 attention, and we correlate these things, we calculate scale dot product. So such as you have heard about something kind of probability over there. You pick a particular word, and in the conditional probability, what you going to do is the same kind of the thing. You compare with all the near related elements, and you calculate the probability. And the similar kind of the idea we adopted here. So here comes the linear layers. So which is kind of the scale dot product attention, where the given elements are stored in a vectorized format. For each and every token, so we mentioned it as we will going to mention some predefined value. We can say this is kind of the hyperparameters. If I tell you that 300 dimension means each and every word should contains the 300 elements over there, 300 values over there. So these will be stored in a single value and so on, and up to the dimension of the my entire text or particular sentence, we will store in a vectorized format. And we have so many vectors over there, such as we can consider as the tensors. And each one we will calculate the linear structure for query key and values. So together we captured the different patterns over there. See here, red color and this light color will capture the different representation, different head representation for keys, queries and values. And then we together perform the matrix multiplication in order to get the scaled out attentions. And we normalize these values using the weight matrix. And then we also calculate the matrix multiplication. After, as I told earlier, we will get some sort of the attention value here. And then we will calculate the dot product with respect to the values. Values here means the actual context, actual content. So we will store in a context vector format. We mentioned it as y1 over here. So this will be the architecture of, we call it as a scale dot attention scores, Sij, we call for each and every index. These are the head representation, 1 to the h. H means this is the predefined values. We mention it as attention heads. We can add more linear layers over there. This is some kind of the hyperparameter one. So that's if we add more number of layers, so it will compute these many times. For instance, if you predefine the 4 heads, it will going to represent the 4 types of the 4 different types of the representation. So this is the major ideology, and which will be in a 2D format. As I told you earlier, the tensor format, and you calculate weight matrix over there. In each queries and keys, and ultimately these will be the weight matrix for the values over here. And for each linear layer, you can predefine the 1 to n linear layer for values, and h 1 to h number of the something kind of n or h you can represent over here, and you compute these values. So which is essential because calculating, so first let us see so how this going to be calculated. As I already told you about these computations, I represented these head representation. 1 to head representations means the number of the heads, and these are the scale dot product attention values. We calculate the multiplication over there after getting the result of queries and keys, and we will get the different type of the projection matrix over here for different heads, and we will contact all together, and we will get the something kind of the dense matrix over here. So the major idea means here So which part of the, I mean, on a higher level, so which part of the token we are giving the more weightage? We have to know, and yeah, we are suppressing the rare ones or less relevant ones of my token, of my target value. So these kind of the weightage is given in this attention based mechanism. This is a major idea of attention mechanism. And then, so as I told you earlier, these will be the head representation. These will be the multi-head because we are calculating the different head over here. So different heads run parallelly. So as I told you earlier, this will be the parallel kind of the sequencing. We run the different heads parallelly. So we run the different heads. I mean, if you run the one pattern, so this will going to call as intra-attention, which can be the self-attention mechanism. So going to be focusing on the each and every input position within the same sequence. This is a major ideology of self-attention, and we run the different heads parallelly. We call it as multi-head attention. And if you choose translation, providing the attention on one document to comparing to the other document, so this type of the technology we do in the attention mechanism on the extension of these kind of the intra attention mechanism here. And this is the diagram of multi-head attention. I mean, so these are the query key values for each and every vectors. We have the different linear projections over here. I mean, different representations, and then we calculate the attention score. And
Sir, I have one doubt.
yeah.
Sir, what is key and what is value as input and what is linear? Please explain.
So I already told you about the query key and value. So query means the word which we are looking for, and the key means the near related one. I mean the other related words which plays a crucial role in order to predict a particular word. So the value means the dot product of the query and key, and then we will compute the scale dot product over there. I mean QK over transpose and root over DK. So which is kind of the dimensionality. We compute some scaling factor over there. So, and then for different representations, so this is a multi-head attention. So each head, we are going to be focusing on a different representation. I mean, you take the text. For each text, you are going to be focused on one particular position. I mean, this kind of the patterns you generate. And then
Yes, sir.
Yeah.
Sir, what is linear there? Linear?
Yes, linear means, that's what I'm telling you. Linear means you compute these type of the attention scores for each representation. You are going to get the different representations.
Okay. Thank you, sir.
And then you will perform the concatenate and merge to get the dense matrix over there. So this is I mean, one kind of the bottleneck approach we can tell. So attention-based approach. I mean, you can see that each and every token which going to be focused on corresponding words. This is a major idea behind this Vaswani attention mechanism, which published in the year of 2017. So how each and every related term focus on the neighbor one within a same sentence, same sequence. This is a major terminology. And these are the multi-head attention. I mean, for each and every head, we have the different representation we calculate over here. So, and then, you can enter these type of the linear layers over here, how much layer you are picking. You can enter in the online. You may change the pattern. So this is one kind of the difference between the recurrent and multi-head attention. In the starting of the talk, I mentioned about this difference between the sequential dependencies and multi-head attention. And again, I'm repeating, for each and every for each and every element, we stored this timestamp, and we are going to input these current timestamp to the next RNN, and so on and so forth. This is the forward forward kind of the RNN. You may call it as forward LSTM. And then you similarly you are going to calculate from n to the 1. I mean, from n number of the text to the initial one. This will be the backward LSTM. And for each and every timestamp, we are inputting to the next one, next RNN, and so on and so forth. This is one kind of the recurrent structure. So here in the multi-head attention, as I told you earlier, and we have the different representation, head representation, we run parallel, and we calculate query key value vectors for each token in a text. See, for each element, we calculate KQV. Yeah, let me check. Yeah, if you have any queries, you can ask me. Okay. Fine. This is one kind of the repetition. I'm just moving forward. I mean, same kind of the representation over here, same type of the computation where we calculate all the value vectors, key value vectors over here. So issues with recurrent models. RNNs are unrolled for left to the right. It encodes the linear locality. So near words often affect each other's meaning. So RNN, so if we want to focus on long text documents, long-term dependencies, very long-term dependencies, and if we want to understand not only one semantic features, but also in a different perspectives, we prefer this type of the attention mechanisms. However, this will be the task specific one, and this is one kind of the complexity over here, order of the sequence length. steps for the distant words pairs to interact. As I told earlier, for each and every time step, we calculate the outcome, we input to the next one. So this will be the order of n time steps. So this is one kind of the bidirectional one we show in the RNN. So for the distant word pairs, we try to interact and as I told you earlier, when it will be the very long dependencies, there will be some, we may lose some of the dependencies if it is a huge chain in structure. So linear order of the words is a major discrepancy here in order to capture, and also we may come over the gradients over there, some sort of the gradient over there, such as whether to choose a smaller step or long step. There will be some dilemma, and lack of parallelizability in RNN. So we pass to the bidirectional by capturing the each and every time step and can perform many independent computation at once. But the future of RNN hidden states cannot capture the fully before past hidden RNN states when it will be the dependency between the terms. It creates the probabilistic. So when the sequence length increases, no longer batch. I mean, there is no longer batches over there. That we can store. So this is one kind of the time steps before a state can be computed, and this is one kind of the high level architecture. So as I told earlier, attention treats each word's representation as a query to access and incorporate information from a set of values. So before talking more about the self-attention mechanism, I will give some basic, some background behind the encoder and decoder model. I mean, these attention mechanism, which is something related to the transformers. I mean, in the transformers, we adapt the attention mechanism. However, the transformers, major focusing on the encoder and decoder architecture. In that, we adopt these technologies. These models. In the encoder, you are going to be encode this representation. You get the you compute the each value. You calculate the some cosine similarity, and you will generate from the feature matrix over there. And in the decoder part, if there is a translation, you look to the encoder part and you take the another input to the decoder, and that's how you compute. You generate the final values from the one language to the other language. This is the major ideology behind the encoder decoder architecture. So the main first model is about the self-attention, which adopts this type of the structure where each word attends to each other within the same sequence, within the input. So these type of the elements, you can see the this type of the hidden pattern, hidden structures, H1 to the HT, and you calculate the attention over there. So means all words attend to the all other words in the previous layer must I mean, these are the arrows must carry forward to the next timestamp and so on and so forth. And the transformer architecture, as I told you earlier, about it focusing on the encoder and decoder channel. And so these are the some metrics or parameters we will going to keep in mind. So regarding the computation complexity per layer, and minimize the path between any pair of words to facilitate learning the long-term dependencies, and minimize the amount of computation that can be parallelized. And this is some kind of the computation complexity where each and every model going to represent. So first, self-attention going to be have the order of one maximal path length, and as I told earlier, and the recurrent going to take the one time step at a time. So we represent O to the power of O of n, big of n order of n time step, and similarly, and we integrate the whole together. We put the whole together, which is a restricted form. We calculate the dimensionality. Between the pairs in each word. As I told earlier, dimensionality means the predefined values. So I represented here D. I included here D. So this is how we calculate this complexity per layer. So this is about the path length minimization and parallelization, and RN based encoder decoder model with attention. So this is RN kind of the structure. You can see this is how some kind of the auto encoding based structure connected with each and every components. So major advantage, each word interacts with each other. So having the attention on each and every element in a sequence. So yeah, this is the architecture of Vaswani attention architecture. Attention, all you know, architecture about the scale dot product attention. In the earlier slides, I mentioned about the scale dot product attention, each and QKV, and then and also multi-head attention I told you earlier. And this is about the main transformer based architecture, encoder and decoder part. It may be around 12 layers. So we will have, and we are going to pass the input, and we have the position encoding here. The position representation for each and every token, and we calculate multi-head attention, and we add the normalization over there, and we mention the skip connections or residuals to move to forward, and or else we will use the for speed up the computations, we will use the feed forward network. So focusing on one direction, and thus we will get some feature matrix over there, and we utilize it, and we if there is a translation kind of the thing, we will going to send, we will going to take another kind of the input over there, and we calculate the pollution embeddings and similar structure, and we will see the encoder. We captured those dependencies, those feature matrix, and in order to correlate my present feature matrix over there, for that, so we are going to add multi-head attention and add an normal, and we are going to calculate the next dense matrix. And if we perform the classification over there, we calculate softmax to get the raw scores to the probability distributions. So this is the thing, which represented earlier. As I told you earlier about how the dimension of the key vector root over D, I mentioned earlier how it's going to be calculated. So which is kind of the predefined value. And then, this is one representation, some sketch over here, how layer 1 going to be capture the inputs and some labelings mentioned. So this is the encoder part. Something kind of translation I mentioned earlier. You can take from one translation to the another translation, some English to Hindi, or Hindi to any other language, French language, something kind of the things. So we already talked about the encoder part. I mentioned, yes. Yes. I already talked about the self-attention mechanism, how it is going to work. And so intuition for attention mechanism. So to look up a value, for the value only we compare the query against the quiz in the table. And you can see this is one kind of the stack over there where the query maps to the one key value pairs. So in the self-attention, each query match the each key, near related one, how these keys are going to create a major impact on query. And we return some of the values and weighted value vectors key match over there. And this is about something kind of the calculation going to done in the self-attention mechanism. And you can see this is one kind of the query key value representation. For each and every term, we calculate these values, weight value vectors. This refers my input term. And you compute the scale dot attention values, and you take these attention scores to get the weighted sums. That's how you are going to get the attention feature matrix at the end. So you have the this is one kind of the attention representation. For QKV, we have the different representation over here. And you calculate the softmax to normalize this value, to stable this value without any fluctuation. I use the softmax. We are going to use the softmax over there. And you take the weighted value of, weighted sum of the values for the further computation. This is about the self-attention so far we covered, and you can refer to the attention is all you need. This is 2007 and Google Brain and Ashish Vaswani. They have mentioned this type of the architecture, and since there is a some kind of the discrepancies, I mean, element-wise non-linearities. We apply the feed forward to the output of the attention, providing the non-linearity activation, capturing the different pattern structures without having only the linear one relationships. We keep we are going to add the feed forward over there. So this is one kind of the feed forward structure, and then so we are going to calculate layer num scale dot product attention to get the raw embeddings for to capture these feature matrix over there, and you calculate the residuals over here for these skip connections for fast transitions moving to the layer normal form or dense representations, and this prevents the network from forgetting or distorting important information as it is processed by many layers. Because of this, we can capture the dependencies, and this is about the layer normalization. You heard about some kind of the normalization thing, sometime kind of the standardization during your statistical ML. You calculate in order to calculate such type of the variances. We are going in that we understood all these kind of the normalization, and the similar concept. I mean, for dense representations, we maintain such type of the normalization over here, and then so there will be the shift in shift kind of the thing when we are going to be train the parameters of a given layer. My given value is going to shift into the another sort of the things. So in order to leverage this thing, balance this thing, so we are going to be normalized to the zero mean and the standard deviation for within the each layer. We calculate ST over here. So this is next we are going to be calculate the scale dot production over here, scale dot attention. So to get the attention scores, in order to provide the weightings to the actual values, we calculate the scale dot production over here to compute to calculate the matrix multiple over the actual values for each and every element. We calculate that these attention, I mean this scale dot attention. So we almost done with the encoder, and you can see this is the some sort of the example. You can see how these are going to be in the feature matrix, how these are going to be transform in the decoder part, how these are useful to for the probability predicting the values over there. So we need to make we need to focus on these type of the representations, and so and then we are going to be, if there is a translation, we are going to pass the another sort of the text over here, and then we apply the position encodings in order to capture the order of the each input value. If there is a sequential dependencies, we do capture all these out of the values. Since the self-attention doesn't build in the order information, as I'm telling about the order information, when we are going to be understand the sequential dependence and sequential structures, we add such type as the positional encoders over there, such that we have the corresponding location index values for each and every element in a sequence. That's how we did the computation over there here. So which deals about the position encoders. Here we captured, but in the forthcoming layers, we rather than focusing on the order of the structure, we parallelly compute these representations. We store in every feature vector over here, and this is my current targeting element. I focus on here related one. This is one kind of the learning positions I focus. Thus, I will going to store in one particular kind of the feature representation over here. So thus we can represent this as the sinusoidal position representation after the computation. I mean, after the encoder positions. What the Vaswani did, they calculated these sinusoidal positions in order to maintain the proper channel. In order to fix it, these kind of the longer sequences, and then this will be some kind of the positional encoding and relation where attention output, and this is a original self-attention output, and the major difference is to capture the relevant position over here. So while dealing with the sinusoidal representations, and that's how we capture these positional dependencies here. And this is the similar thing, I mean, where we reside in the layer. So it highlighted, and then encoder representations, ENC, the soft, I mean, short form here, and multi-head attention. And during our discussion, I mean, we talk more about the multi-head attention representation, about the value key vectors. I mean, for different representation, we have the different heads. Thus, how we calculate the structure. So the idea behind this MHA, I mean, you can see which is some kind part of the, you can see the overall architecture over here. I mean, where we did this multi-head attention. I mean, Vaswani, they mentioned here, I mean, these kids, the interchanging one, I mean, the self-attention and the multi-head attention. I mean, similar concept over here. I mean, we run the different representation in parallel in the multi-head attention mechanism. And see, we compute we are going to repeat each steps. Such as we do the scale dot projections and matrix multiplication. That's how we will get those computations. If you take in any text, so for each and every token over there, so we are going to be stored in a vectorizer format. So for instance, if you take BART encoder, BART representation transformer, bidirectional encoder representation transformer, in that which is kind of the PLM. So in that you are going to be focusing on each and every input position, and then you mask the around the 15% of the tokens, and depending upon the surroundings only, you are going to be calculate the mask positions, mask tokens, these positions. So which is some kind of the auto-regressive fashion. You compute in the bidirectional way, as like we did in the BIOLIST. Here we have the time stamp. We focus on the timestamp for each and every token. That is how the BART mechanism focusing on such type of the terminology. And then these are these structure, but structure going to be adopt this type of the self-attention, which is nothing but here means the multi-head only. Why? Because we calculate the different representations for each and every word. Going to be stored the different representation. Representation means here means the elements are going to be changed. The numerical value is going to change in a different patterns. If you take the 4 heads, going to have the 4 different computations, 8 heads, and so on, so forth. So in that we are going to be extract those feature representation, feature matrix, the part of the encoder run during the BART mechanism. What I'm trying to say that BART mechanism going to be, pardon me. Okay, anyhow, so in the BART mechanism, these MHA, multi-head detection, plays a crucial role. So in order to predict the masked dependencies, and then we may come over these type of the multi-head detection plays in the crucial role. If you take the extension of the BART, and you may choose the robot district BART, and also which plays a major role in XLNet and etc. And even the LLMs also. Some sort of the most of the llamas and llama based structures, we also use this type of the format, and then this is a very vast one. Understanding this attention mechanism, and then moving towards the soft attention, self attention, and then multi-head attention. So this is a very vast one, and we need to get better intuition to work in the to work for LLMs. So So, one second. We struck this slide. I mean, so we have understood about the how the value. I mean, how this component works. How this feature values works. Value vector works, and then this is one kind of the that is how we have captured the entire encoding structure, and these are the predefined one. For the number of the parameters and so on. So in the decoder part, so as I told earlier, we are going to get the one more multi-head block, because we take the new input and we look into the encoder part. So for instance, you take conversion of so Telugu language to the English language. So you pass Telugu language as the input, and you will get some of the features over there, feature matrix over there. Then you are going to be pass the English language, and you calculate the similar computations. You will get some sort of the feature matrix, and you look into the previous encoder where you get the feature matrix, and you map these related things by using some kind of the dictionary. You build a dictionary over there by understanding each and every token, each and every element location, and then you compute the attention scores. So this will be the something kind of the this will be the attention one. Attention mechanism, pure attention mechanism. In that we have these components. The multi-head attention. Which is kind of the you compares with the document from taking a document from one language you at a hand, and you compares with the other language, and then taking the document from the different language. So that is how you correlating between the one text sequence to the another text sequence. What I try to say that so we discussed earlier, self-attention, which contains the attention over there. Focusing on each and every input position, with the near related ones within the same sequence. Sequence means which is the dependency between the words, or you can take if it is not something kind of focusing on that, you may take certain types of the sentences focusing on within the same sentences. So this is the one thing. And the next one is the if you run these into the different head representations, you calculate the multi-head attention, you calculate the pair of query key vectors, and you calculate dot product, and you calculate and this will be the weight for my value vectors, the actual value vectors over there. And that's how you came to know the attention scores. So thus we are going to understand which sort of the element, which sort of the in a higher level, which sort of the word we are going to be give a more attention. And if this is a semantic related one, near related one, we give the high priority, and we suppressing the near related one, maybe we will give the low weightage. I mean, we give the low weightage to the rare one. If it is a near related one, we give the higher weightage. So this is kind of the thing we will analyze at the very end of the attention mechanism. And then what I'm trying to say that either self-attention or multi-head attention going to be focused on within the same sequence, but not the focusing on the different sequences, which is a part of the this entire architecture. I mean, if you take the attention mechanism over there, if this transformer architecture adopts my attention mechanism, and then going to work on both the sequences. One is the my input sequence going to work, and the target sequence going to perform the different computations over there. Similarly, we will calculate after getting the feature matrix over there, we will calculate same sort of the query values. I mean, by we are getting all these weight matrix over there, we calculate, we extract from the previous encoders. We look and we map just decoder, which is kind of the mapping the things from the looking back to the encoder and getting the knowledge from my current input, and finally you will going to get some kind of the raw scores. I mean, from numerical values, a dense representation, and then you calculate the softmax over there. And as I told you, for the for maintaining such type of the scalability without I mean, balancing purpose, some predefined values we put without crossing, without getting such type of the high dimensional values, and we calculate probabilities over there. If it is a classification kind of the thing, we calculate the probabilities, and we will get the ultimate sequence, that is the translation from the Telugu to the English translation. This is the main idea behind the encoder decoder architecture given by the Ashish Vaswani, and so this in the meanwhile we are going to have the skip conjunctions, I mean a residual ResNet for faster computations. You heard about the ResNet over there. I mean, when we are dealing with the LXNet, I mean, not the LXNet, ResNet over there, for the faster computations, we move forward by using the normalized one, I mean feed forward one, and we that's how we compute this structure. And then if we have a language modeling objective, can't the network just look ahead and see the answer? But we can't actually agree with sort of the thing, because we have to map the my given input sequence, I mean to the target one, without knowing that how we can translate these things So we can't map these things. We can't get the target sequence, actual sequence. That is why we are using this attention mechanism. And then if we have the language modeling objective, as I told you earlier, we use the something kind of the masked attention mechanism at a high level. We hide the information about the future tokens from the model. And the masked attention mechanism I mentioned while using the BART structure. We are going to be mask the certain tokens about the 15 percentage. This is kind of the generation 1. Language generation 1. So you have to we predict these 15% tokens by understanding the near related tokens, and we predict these 15% words, and we apply the masked attention mechanism. We mask some of the elements over there, and we calculate the so query key value vectors. We perform the scale dot productions, and then we calculate the normalized codes, root over dk over there. We compute the v dot product to the value vectors, and then we will get some weightings over there, and using this we predict the next token. What I'm trying to say that this is one kind of the autoregressive one. We use the something kind of this understanding the near related one, some kind of the bidirectional dependencies, and which we have seen in the bidirectional LSTMs. For each and every element, we calculate, we pass the input, and we compute. You analyze the architecture of the LSTM over there. We have the forget get, input get, and the output get. What it tries to provide, keep only the important one, and then suppressing rare one, which is the non-trivial one, so suppressing the non-trivial one. So this is the one kind of observation which we had earlier in the bidirectional RNN. Bidirectional kind of structures. It could be by LSTM or by GRU, etc. And in a similar fashion, what I'm trying to say that we use this type of the mask attention mechanism mostly in the BART layer, BART kind of the architecture, PLMs over there, and pre-trained language modelings over there. And then we use the similar architecture for a robustly optimized BART mechanism, Robota, and the XLNet. We use the both the auto regressive fashion and the auto encoding, and also regressive fashion. Means I told you earlier about the understanding of the conditional probabilities, and similar concept we adapted in the auto regressive based transformer modeling. Same thing, means the one particular element going to be focusing on the other elements. Thus we have something kind of the pipe signal over there. Means we calculate the conditional probabilities over there, and this is how we calculate the mask retention mechanism, mask structure. I mean, you can see, I mean, we use this kind of the BART mechanism mostly for the feature representation. And when encoder representation only for capturing this type of the embedding structures, you calculate scale dot product over there. You compute with the dimension values and root over decay for each and every QKB values. It will going to change these type of the predefined values you mentioned, and thus this is one kind of the embeddings over there. And you mentioned the normalization scale dot I mean not normalization over there. So to get I mean to get the scale dot computations over there, and then to understand the we pass it to the multi-head attention to get the intuition behind the different representations, and to get something kind of the dense structures. You normalize these things, and means I mean W over O, we calculate, we tell it as the orthogonal projections. I mean, something kind of the reduction, so these are the something kind of the high dimensional values, and you add this type of the structures over there. And in the meanwhile, you add these skip connections. You directly pass to the one block to the another block. Why we are adding these two blocks? Because this focusing on my current decoder position, and also my previous. I have to look into my encoder one, so that I can map these structures. These are the something kind of the embedding structures. And then so this is like we have seen the image in the scale dot product, I mean, which is one kind of the scale dot product. I mean, you calculate mask retention, matrix multiplication, so linear layer, and the same kind we have. So these kind, so these structure, I mean these attention based or self attention based structure, we have the many structures. I mean, in a deeper concept, I'm telling you, I mean, for each and MHA, you have to just analyze those I mean self-attention architecture, which I have shown you earlier. So you have to just analyze those architecture. Thus, how you come to know how each layer, I mean, how each element which is different, how it is differently getting this representation. So the major idea is to know the different patterns. We have to generate the different patterns. Thus, we don't want to lose such type of the we can say the contextual dependencies. The major aim of these attention-based mechanisms. So in which context my current input going to be focused on. So we need to figure out those contexts, which is a crucial one, in order to understand the ultimate overall emotional tone. If you want to predict an emotion of a document, so this is the major crucial one. So then ultimately we perform the softmax over there for Roscoe to the probability distribution, and that's how we come to know about the translation of one language to the another language. So as I told earlier, this is about the something kind of the you can see that this is one kind of the encoder part. This is the decoder part. You perform you pass some kind of the input, and the outcome of these each and every feature byte is going to input to the my decoder part along with the current input. You can assume that this will be looks like the something kind of the RNN part, but which is kind of the auto encoding based structure. It is how each and every interlinked with each other, and so we discussed all these things. We understood all these scale dot product structures. So we apply the self-attentions and the different self-attentions together. We call it as multi-head representation. That is how we are going to run in a parallel. So just we are passing to the one particular layer to the another particular layer. The feed forward tells like that. So and so as I mentioned earlier, if you want to search a particular query, and each query you will have to compare with the near related tokens. We call it as different keys, and then which are stored in an index, just like framing like index. And the ultimate aim is to compute these, see how the mathematical intuition behind this. You can take you're calculating the q into k0 and q into k1. So for each things, you are going to be write math over there, and then this is kind of the dot product attention. And then you on the top of that you pick from a value vector over there, and you will going to be have this as the weight matrix. You compute the weighted sum over there. And what I'm trying to say that so for each word you have the three different vectors, three different weight matrices, such as query q, query key and value for each and every element. In a higher level, each and every word we have these type of the representations, and then we calculate the dimensionality dimension over each and every query key values, and this key keeps changing. If you take the self attentions, if you run the different self attentions parallelly, and this will be the something kind of the, I mean, this will be the multi-head attention. So, and then I discussed about the skip connections, and so we calculate something kind of root over decay, these normalization scores. And this is the batch size of the tree samples. We calculate all the feature values. This is one kind of the example. And then you see that this is one kind of the self-attention structured. I mean, for these MHA mechanism, we focus on, we have to analyze these self-attention structure, how we are going to be captured, how we are performing. We take the Q and K, we calculate matrix multiplication, we solve the scale dot projections, and we in order to leverage these dimensions, we apply the root over decay over there, we apply the softmax, and then we on the top of that we apply the matrix multiplication, Q to K to the power of T, we over I mean, so we divide with root over decay. So this is one kind of the scaled out attention transformation, and then we apply the value. So the context one, and we calculate the matrix multiplication over there, and so this is the self-attention architecture, one kind of self-attention architecture. We will going to be, I mean, we are going to be have just we run parallelly this architecture. So these are the things we already covered earlier, and so we are here, and I mentioned about the masked attention mechanism. That's how we have, I mean, just revised these type of the concepts, and meanwhile we have come over all these matrix multiplication structures. So these are the crucial one. I mean, these are the related to the each self-attention, and then you are moving towards the multi-head attention, and so you try to calculate the masked attention over there in the meanwhile of the multi-head self-attention, which is called as the multi-head attention, which is nothing but the MHA. And then so this is something kind of the scores we have. I mean, which sort of the text we are going to be focused. Something kind of set of the query and case, and this is how going to be represent the minus infinity to mask out the attention to future words by setting the attention scores. This is something kind of a masked representation. We are going to be understand these by understanding the attention features. We are going to fill up these masked attention values, and this is how we have understood the encoder decoder architecture. We have represented in the dimensional over D for each and every representations, and then this is about the decoder. We finished just we focused on decoder, and then finally we will get the logics or the ROS codes for probability distributions. This is the architecture. I already went to the architecture. I already we have discussed enough about the architecture, and these are the links where you can get to the all this position representation and quadratic computing self-attention, and this is about the performance of the linformer. So previously they did this type of the attention features. You may revise this kind of the architectures, and this is about the parameters. They have taken something kind of the chart. Yeah, you can visit the attention all you need paper, and you can visit the Harvard EDU for annotated co-transformer, and that's it. This is some kind of the acknowledgement. You may refer this textbook, and if you need, you can go for you can revise this textbook, or you can choose the Ian Goodfellow, and that is the end of the talk. And thank you. You may have any questions. If you have any questions, you may raise. And thank you all.
Thank you, sir.
Yeah.
Thanks a lot, sir. Such an informative and detailed session, sir. Thanks a lot.
Yeah, thank you very much for inviting me for the talk.
Dear participant, do you have any doubts? Okay. Vasanta madam?
Sir. Yes, sir, I'm here. It has been a truly insightful session today, and I take this opportunity to express my heartfelt thanks to our speaker, Dr. Dheeraj sir, for his invaluable knowledge on natural language processing. Your in-depth explanation of attention and intuition and different types of attention mechanisms like self-attention mechanism, multi-head attention. At the same time, the architecture of the attention mechanism and the recurrent models, and what are the issues we are faced with the recurrent models, and minimization and parallelization techniques, as well as encoder and decoder techniques, transformer model, architecture. Your words have left us with a great learning takeaways. Thank you once again, sir, for sharing your valuable insights. Thank you, sir. Thank you all.
Thank you very much for your participation. Thank you all. And I will going to take the leave, and bye.
Thank you, sir.
Thank you, sir. Thank you very much.
Good night to all of you.